Okay, problem 53. Determine which of the following functions would have vertical asymptotes of x equals plus or minus 2 and a horizontal asymptote of y equals 0. Okay, now vertical asymptotes are going to make their discontinuities and make the denominator 0, provided that they don't share the same common factor on top, which we learned back in the first part of the course. That's talking about the removable and non-removable discontinuities. Essentially, the one-sided limits those points go to infinity. So if they shared a common factor, then that would not be, it would be a discontinuity, but it would not be a vertical asymptote. It would just be a hole. Now, the only one that kind of satisfies this right off the bat is the C, because x squared minus 4, and there's no common factor on top. So those will be the vertical asymptotes. So I really didn't need this next part, but the y equals 0, that comes from the fact that we've learned this back in the first part also with limits, that the limit goes to 0, as x goes to infinity equals 0. That gives you the horizontal asymptote for y equals 0, so clearly that function would satisfy those properties. All right. 54. The product of two positive numbers is 675. Minimize the sum of the first plus 3 times the second. So I wrote this as, the choice of the letter S is purely arbitrary. You can use any letter you want here, but the x plus 3y is important, or whatever letters you use here. They don't have to be x and y, but it's x plus 1 plus 3 times the other. And we know the product will be 675. So when you multiply them together, they'll be 675. So what I'm going to do then is I need to have a function of a single variable. So this is our objective, and that's our what we call constraints, one way to call it. Or the book uses the terminology primary and secondary equation. So I want to get this in terms of x. You could actually do it in terms of y. You still get the same, you get correct two numbers, but I'll do it as a function of x. So I'll take this equation or the product over here, and I'll solve for y equals 675 divided by x. And I'll substitute that in there for y. So we have 675 divided by x. And then multiply it by 3. And I went ahead and brought the x up. So your function, we're going to minimize as a single variable x, will be x plus 2025 x to the negative 1. So we take the derivative. Derivative of x is 1. Bring down negative 1. Change that to negative 2. And set this equal to 0. So when you're setting this equal to 0, it makes it much easier to drop that negative exponent back down to a positive. So I'll move this, lots of ways you can go about this. Looks like what I did here was I multiplied everything by x squared. So it gives you 0, it gives you an x squared, cancels the x squareds here. So then you end up basically with x squared equals 2025, which means it'll be the plus and minus square root. Now, I've talked about this in other videos that, very important to understand that when x squared equals a positive number, you have two solutions. Mathematically, there are two solutions, a plus and a minus. But I crossed out the minus because a lot of times in these optimization type of problems, there's reasons why you would not include a certain number. But when you're doing graphing and sign charts and stuff, you want to include every number. This one, because it clearly says here, two positive numbers. So this really would have been plus and minus 45. We don't need the negative 45. We want the 45 only positive. And then we know what x is. So to get y, we can come right back up here where we have y in terms of x. Take 675 divided by 45. That gives you 15. So your two numbers in are basically 45 and 15. That would satisfy that constraint. And the smallest possible result you can get from x plus 3y. Now we want to find two numbers whose product is a maximum if the sum of the first and 5 times the second equals 80. So it's a little bit different this time. So instead of giving the product and minimizing the sum, we actually have the sum and we're trying to maximize the product. So I'm just using P as the variable to represent product. And then I know that first one is x plus 5 times the second y equals 80. X equals 80 minus 5y. Now I did something a little bit different this time. In other words, I went ahead and solved it in terms of y, which is perfectly fine. I guess it just didn't feel like messing with the fraction. I could have solved for y in terms of x, and I go, well, yeah, solve it this way. I don't have to worry about a 1/5 or anything like that. So either way, we'll still get the correct two numbers. So if x equals 80 minus 5y, so now you notice I'm labeled this p as a function of y. So x is 80 minus 5y times y. Distribute that, you get 80y minus 5y squared. Take the derivative, which is 80 minus 10y. Set that equal to 0, because these are always coming from the critical numbers, these answers, and then from the maxes. Always coming from the critical numbers. So you solve that equation, which obviously is easy. You get 8. And then you plug in x equals 80 minus 5y, plug in 8 for y, you'll get 40. So one number is 40, the first number is 40, and the second number is 8. So had we done this the other way, solving for y in terms of x, I would have then gotten 40 for x over here, and then plugged it in and got 8 for y. So we would have got the right two numbers either way. So 40 for x, 8 for y will guarantee we get a sum of 80, and that's the only two numbers that will add up to 80 under this equation that will give you the largest possible product. Now you can make up other numbers for x and y that satisfy this equation, but I guarantee you if you put it in this product equation, it'll be a smaller product. And so what would our product be? It would be 40 times 8, which is 320. That would be the maximum profit. So there's no way you're going to be 320 if you pick any other numbers and put it in there. Calculus guarantees you will not be able to do that. All right, we've got 300 feet of fencing, and we're bordered along one side by a river, so we're not worrying about fencing the riverside. And we're going to find the dimensions of the pasture that will produce a maximum area. So what I labeled, now you could, the choices of x and y do not necessarily matter here. You'll still get the right dimensions. The two matching sides will be the same number, and the other side will be a different number. But in other words, if you did 2 y's here and then an x on the long side, that would still come out okay. You'd get the right dimensions. But I just chose to write it this way. Might have made more sense to you to do it the other way if you're looking at it from a vertical or horizontal standpoint. I wasn't looking graphically, in other words, I wasn't looking at it that way, so it didn't matter to me. So I just put 2x plus y equals 300, and I let y equals 300 minus 2x. And here's the area that we're trying to maximize. Just x times y, pretty easy. Area of a rectangle. So I'm going to substitute y equals 300 minus 2x in for y, and then I'll have x times 300 minus 2x. Right. Now, it certainly would be way too much trouble for this to do the product rule to get the derivative. That'd be a little silly when all you got to do is distribute the x, and you got it. So if you distribute the x, you have 300x minus 2x squared, and then we take the derivative of that, which would be 300 minus 4x. Come down here, we'll set that equal to 0, all about setting the derivative equal to 0. We will get 75. And then the long side then will be, so we know that it's 300 minus 2x, so it'll be 300 minus 2 times 175, which equals 150. So let's suppose that then the problem asks, okay, what would be the maximum area? That's the actual dimensions. 2 75s and a 150. Like I said, you would have got the same thing. Then you would have got, reversed them, you would have got x is 75 and the y's, or I mean, x is 150 and the y's would have been 75 if you reverse the variables. So then if it asks for the maximum area, all you have to do is multiply those two numbers together to tell you what the area actually is. This is a similar type problem, but the only difference here is we want a specific amount of area we're trying to obtain. We want to have 20,000 square feet. Then we want to know, okay, what's the minimum amount of fencing that must be used to enclose the remaining three sides. So this is different than the last one, where we had the perimeter, we knew the length of the fence, and we want to maximize the area. Well, now we're trying to minimize how much fencing we have, because it makes sense. You want to minimize the cost of the fencing in order to still get 20,000 square feet. Okay, so now we have that x times y will equal 20,000. You see I kind of labeled them the same way I did the last problem. I used p for perimeter, but that's not real critical what variable you call that, but this part is. But it would be, if you add that up, it'd be 2x plus y. So y would equal 20,000 divided by x in this equation. So it's 2x plus 20,000 divided by x. So I would bring the x up. That's just me to take the derivative. It'd be silly to do a quotient rule here. Bring the x up, make it -1. And the derivative of 2x would be 2. -1 times 20,000 will make -20,000. X to the -2. Set that equal to 0. And then when I set that equal to 0, notice I do what I always do. I immediately drop that back down to make it a positive exponent, because it's algebraically easier to deal with, I think, than a negative would be. Okay, so if I move this over to the other side, there's several ways you can go about this. So you have 20,000 over x squared equals 2. Cross multiply. So you have 2x squared equals 20,000 divided by 2. So you get x squared equals 10,000. So once again, mathematically, there are two solutions that satisfy that. -100 and +100 would satisfy that equation, but we don't want -100 because we're measuring length, and it would be silly. So I don't think this one, unlike the few problems ago we were doing the two, so the numbers are both positive, find this, that stuff. Here, common sense tells you it can't be negative because we're measuring length. Now, just for grins, I did this here. Usually aren't required to show this, but you might say, well, how do we know for sure that that did produce a minimum? How do I know that that's a minimum value? Well, you could use the first derivative rules with sign charts and all that kind of stuff, but I just used the second derivative test. I took the derivative of this first derivative, would be -2, would be positive 40,000, two negatives, x to the -3. And if I put 100 in there, basically it's 40,000 divided by 100 cubed. But either way, that's going to be a positive number. I didn't indicate what it was, but obviously it's positive, something greater than 0. And the second derivative test guarantees that's going to be a minimum. So it is a minimum. I just did that. If you don't have to do that, but that's how you can sort of verify, hey, how do I really know if this is a minimum or maximum? Okay, so y up here is, if x times y is 20,000, y is 20,000 divided by x. So 20,000 divided by 100 is 200. And therefore, so x would be 100, y would be 200. So long side 200, 100 on each short side. So now we know the smallest amount of fencing that we can use to get our 20,000 square feet that we want would be 400 feet of total fencing. So save us how much we have to pay in fencing costs. All right, here's one where got two adjacent pins. I believe I have one just like this in my notes. This is labeled X's and Y's. So even though you see Y's up here, there's also, when you're talking about the perimeter, there's two Y's on top. But the area is just 2xy. In other words, there's two ways you can look at it. You can say, you ignore the width of the actual fencing. That's not a factor here, but you can look at it as y plus y equals 2y times x, which makes 2xy. Or you can look at it as two separate xy's added together. So xy plus xy would be 2xy. So Either way, you get 2xy as the rectangle area of the two rectangles. We have 400 feet of fencing to make this happen. So there's 3 values of x, and like I said before, there's 4 values of y because there's 2 up on top, also that when you measure that didn't affect the area, but it does how much fencing we have. So that's why we have this equation. Looks like I got this. Must have been working with a different picture here because, well, actually it won't matter, but looks like I did this with the x's and the y's reversed, but I'm not going to change it now. But the area would still be 2xy even if you reversed them. Well, let's just go ahead and go with this then. But technically it should be reversed. So 3y then would equal 400 minus 4x. So then divide by 3. So y would equal 400 minus 4x divided by 3. And then so we substitute that in for y. So we have 400 minus 4x divided by 3. All goes in for the y times the 2x. So this one you want to distribute. So 2x times 400 divided by 3 would be 800x divided by 3. 2x times negative 4x over 3 is minus 8x squared over 3. So we take the derivative of that. And we would have, so 800x over 3, the derivative of x is just 1, so it would be 800 over 3. So this one would be 2 times 8 is 16, so it's 16 over 3 times x. Set that equal to 0. First thing I did was multiply by 3 to get rid of the denominator. So I get 0 equals 800 minus 16x. 16x equals 800. Divide by 16. 800 by 16 would give you 50 for the x. And then y we have in terms of x right up here. So you put the 50 in for there. We get a fractional answer here. That's fine. 200 over 3 is good enough. Or 66 times 2/3. So this is still fine numerically, but so basically these vertical values are really the y's. They're 66 and 2/3, and then you have each of these y's here where the x's are 50. So you have 50 along the side and 66 and 2/3 vertically. They're still multiplying the same numbers together. It would still be 2 times 50 times 200 over 3, even if the x and y are reversed. It'd still be that exact same product. So that ends us up with, or whatever, obviously it may be a decimal answer. So 20,000 over 3, which is, I guess, 6666 and 2/3, something like that. 6,666 and 2/3 square feet. And I just took the second derivative, and that was just a negative number. Easy, there's no x's or anything left. Negative less than 0. That's just what guaranteed it's a maximum. So, all right, sorry about the reversal. I don't know what happened here on those variables. Didn't mean to try to confuse you there. But the good news is it did not really hurt anything here. All right, so here's the classic folding up the corners of the box, which is in my notes, and certainly put this one on test before. Now I come down here. They're 12 inches, I believe, all the way around. I know that doesn't look, they don't have to be the same. It doesn't have to be a square. The picture doesn't show that. I mean, you're cutting off square corners, but they could actually be different dimensions. But this is 12, so it should be more square shaped. I don't know why it's rectangular looking. Anyway, no, I can't grab and fix that, but no harm. So if you're cutting off x off each corner, and then you're cutting that off, folding up the flaps, and you're making a hollow box. So if the whole length is 12, the entire length of each side is 12, and you're subtracting x from each end, that means the part that's not cut out will have a 12 minus 2x measurement. So the other side will be 12 minus 2x. So you sort of have to visually imagine So your volume is length times width times height, but we need this in terms of a single variable, not three variables. And we certainly have that as, so it'd be length, width, they're both the same, 12 minus 2x, 12 minus 2x, and the height is x. So if you think about it, see that's x right there, just like it is, x, x, x all the way around. When you fold that flap up, it'll be x high. So you just sort of envision that folding up and having a height of x after it folds up. All right, so once you do that, oh, one thing to keep in mind in this problem too is that, right there, like something got cut off here, didn't it? I don't ask necessarily to identify the domain, but I do want to mention this because well, I'm certain obviously you would realize it has to be positive numbers. That's not the issue. What the issue is here is that you're even limited on what positive numbers you can have, because so it's got to be greater than 0. We realize that. But let's think about where am I getting that 6 from? All right, I'll tell you. Just imagine if x was 6, exactly 6. If you cut 6 off from each side and the length is 12, you have nothing left. You've cut the whole thing. So technically it has to be a number less than 6 but bigger than 0. It'd be like 5.99. Now it would be a very silly looking box if you cut that off and be super, super thin, but mathematically it would work. So as long as you stay less than 6, so basically it's whatever that side is divided by 2 every time. That would be the maximum. So obviously any domain values that are, so we would actually toss out positive numbers also instead of just negative, anything that's not between 0 and 6. All right, so let's see. Take that first two, FOIL them out. You'll get this right here. Multiply that by x, and I just kind of rearrange the terms. That gives you 4x cubed minus 48x squared plus 144x. We take the derivative of that, which would be 12x squared minus 96x plus 144. We'll set that equal to 0. You could even graph it in a calculator and find the x-intercept if you want to. Maybe, but I'd go ahead and solve it this way, though, because these always end up being factorable, so it's not that bad. But it looks like a big old monster there when you set that equal to 0, but they share a 12. You can factor a 12 out of there. And then when you divide by 12, you still have 0 on the left side. So then you're left with a much easier thing that does factoring. So these always factor for this kind of problem. So that factors into x minus 6, x minus 2, which gives you 6 and 2. We cannot use exactly 6 because of what I just explained. So 6 is no good. Throw it out. So 2 has to be our winner here, assuming it's done correctly, which ours is. So watch for that one. So you'll get two positive numbers, but one of them is cannot be used. So if you know that x is 2, you can figure out the other dimensions real easy because the other sides will be 12 minus 2x. So 12 minus 2 times 2 is 8. So that means the dimensions are 8 by 8 by 2, which would then give you a maximum volume, 8 times 8 times 2, 128 cubic inches. So if you cut off exactly 2 inches from each corner, that will give you the maximum possible volume inside that empty box when it's folded up. And that's the beauty of calculus. Find the point on the graph, y equals the square root of x plus 1, closest to the point 3, 0. Now, I don't know why I have this dot drawn here because so our point's 3, 0. There's our curve, so we're trying to minimize the distance. So, it wouldn't have been where I drew it, that's for sure. I mean, you don't have to draw it to know where it's going to be. I'm just giving you an idea here. You figure it's probably going to be somewhere about maybe right there, the closest distance to this point right down there. So you start going back that way to the left, it's farther away. Here it'll start moving farther away. So probably somewhere in there. But the good news is we're not guessing, we're using math. Now, distance formula. And you can look at, there's examples of these in my notes for sure. Basically using the distance formula, x2 minus x1 squared plus y2 minus y1 squared. So essentially, here's what's happening. This doesn't really matter which one is which, but I just wanted to. That is my x1, y1. Trying to freehand a comma here. That's not too bad. So that's x1, y1, and then this will, and then x2, y2. Now the way you look at x2, y2 is you treat x2 is essentially x, and then y in terms of x is the square root of x plus 1. So that's your actual point for that graph. So any point on that graph can be represented as x, comma, square root of x plus 1. And then this one's 3, 0. So using then that x2 minus x1, x minus 3, so I have x minus 3 squared, plus y2, which is now in terms of x, the square root of x plus 1, minus y1, which is 0 squared. Now, you can get rid of the square root here. Now, obviously, if you're trying to find the exact distance, you need the square root. But if we're just trying to find the value that minimizes that distance, the reason why is you can just pretty much ditch the square root, because if you're minimizing the quantity under the radical, you're also then minimizing the quantity with the radical. So that's why to get x, you can just get rid of that radical. But like I said, though, if you want to calculate the actual distance, you would then need to plug it in with the square root. But so you can just, to get your value, just I wrote the radical there to show you, but then yeah, where I wrote minimize the quantity. I think in the notes maybe I wrote like d star or something. I've done that before. Maybe I haven't. Maybe I got rid of that. Where just kind of, if you put a d star, you're giving it a different variable name, and so just it's not really d anymore because the square root's gone. But we're minimizing under the radical. So you FOIL this out. X minus 3 squared would give you x squared minus 6x plus 9. Remember, we got to square a binomial. You got to, it's not x squared plus 9. That's incorrect. Over here, we subtract 0. Nothing's happening. So square a square root kills that out. X plus 1. Combine these terms, and you get x squared minus 5x plus 10. So then we take the derivative of that, which would be 2x minus 5. Set that equal to 0. We get 5 halves. So the y is x, the square root of x plus 1, right? So it would be the square root of x plus 1. So it would be the square root of 9 halves, or I don't know. It's possible if it was multiple choice, they might try to simplify that radical or something, but I'll show you that real quick. I don't really care on handwritten about rationalizing denominators. That doesn't mean anything to me, but so it would, certainly look like this. The square root of 9 is 3. But then you might be looking for this as an answer, because it might do this. So it's possible you might would see the y coordinate as 3 square root of 2 over 2. Same number. Of course, you could also check with a calculator which one was the same, decimal equivalent. That would do it too. Usually we don't ask for what the distance actually is, but then you could get it, because if you want to know, okay, that's the closest distance, what is that distance? Well, what I would do, instead of plugging in the entire distance formula, is here we already have it simplified right here. So if you put 5/2 in for that x in those two places right there, but then you've got to square root it. So you put that number in there and then put a square root over it, and that would be the actual distance. Because even though that says d, well, it's really tempting to want to give that a different name or something, because it's not really d if you ditch the radical. But then that would do it. Plug that in there, and then you would take the square root to get the actual value for the distance. Okay. There's your coordinate. About, it's pretty close to where I drew it. 5/2 for x. Okay, now we're getting into the differentials. Now this can be a little confusing because it's easy to mess this up with related rates, but this is not related rates because it's telling you it's differentials. And all differentials is when you take the derivative. If you took the derivative of this function with respect to r, dv, dr, and then move the dr over to the other side, that's what differential form is. So if you took this derivative as normal, so no rates of change with respect to r as your variable, you would get 4, so technically it would be dv over dr, dv dr equals 4 pi r squared, and then you're just bringing the dr over. So what we do here is plug in. Let's see what we have here. We should have a value for r, which is 3 inches. And then the dr part, that's going to be the measurement error, or the possible, range of error on the measurement. So within 0.01 inches means plus and minus 0.01. Maybe it's possible a question might not actually have the point plus or minus. That's okay too. So 3, then you put the plus and minus 1 right in there. Plug that right in there. There it is. Plus and minus 0.36 pi inches cubed. Now I just left pi there. Now of course it's possible that the multiple choice answer, on the test would have, whatever 0.36 times the value of pi. That's very possible. But in a handwritten test, I wouldn't. Leaving pi there would be fine. So it's possible this measurement, of your volume could be off by whatever that is. 0.36, that'd be a little over 1. 0.36 times pi. All right. Cube, volume of a cube. It's easy enough. So let v equals x cubed, and you're take the derivative of that, which basically is dv dx equals 3x squared, and then you're bringing the dx over, so it's dv equals 3x squared dx. So this time they're not giving us the value of x, but they're giving us a means to find the value of x. So instead of telling you what x is, they're telling you the volume is 27, so we can get x, because then 27, v equals x cubed, 27 equals x cubed, therefore x would be 3, cube root of 27. So we were able to get it. And the volume measurement, so that's giving you the dv here, within 0.027 cubic inches. I guess I could put a plus and minus there to be perfectly correct here, precise. And then we're solving for the error in the measurement of the side of the cube, the dx. So we have 0.027 plus or minus equals 3 from right there. That 3x squared, x is 3, 3 times 3 squared. So you divide both sides by 27, you would get plus or minus 0.001 inches. So this, I could see, if we weren't careful, this could have been messed up by, I could see someone putting the 0.027 in for the dx and solving for the v, but it says volume right here. Then also use the units. The units tell you they're cubic inches, meaning that would definitely be the dV and not the dx. The dx would certainly be a linear measure. So be careful with that. Other than that, it's not that difficult. Okay, now it's here. So now you're just doing this from a function. These formulas are always given on the test for this, so you put them in there somewhere. The delta y and the dy. Now the dy is actually an approximation to delta y, so keep in mind your answers need to be pretty close together. Let's see. Okay, so it doesn't matter which one you do first. And delta y is basically just f of x2 minus f of x1, or f of x plus delta x, which delta x can be negative. You could be, the function could be going back to the left. But here it's positive. So basically, x is 2, delta x is 0.1, so 2 plus 0.1 would be 2.1. So that's where that's coming from, 2 plus 0.1. So f of 2.1 minus f of 2, so you see I did it right here in the calculator. So you put it literally, you're putting in 2.1 cubed minus 2 times 2.1. There's the first part. The next part is 2 cubed minus 2 times 2. So you're just plugging 2 points, just like you would evaluate any function. Plug in the value for x, plug in the other one, subtract. It says 3 decimal places here, so on a handwritten test, I would expect you to use zeros, like I added zeros there. Then once 3 decimal places, make sure you put 3 decimals, even if there aren't any decimals there. All right. So let's see what happened now. The dy, the differential, is just found by dy equals f prime of x dx. That's your standard differential function equation. Like saying dy dx equals f prime of x, but with the dx moved over, which it certainly does. Dy dx does equal f prime of x. So the derivative of the function then, right here, so there's your y. Dy is actually, this is a little confusing here because this is correct, 3x squared minus 2, but that might make it appear that it goes on the left side. So maybe, because the dy is what you're always solving for here. Maybe I could add in here, maybe without messing this up too much. If I call that f prime of x, basically, or I don't know if that will help. But anyway, the 3x squared minus 2 is the derivative is going in here for the f prime of x. Maybe I'll add that at the end. In other words, this equals this part. So the dy is always on the left side. It's not going. That's the f prime part. 3x squared minus 2. Try that equal sign one more time. Okay, so I could see where that would be a little potentially confusing. But it's just the derivative of the function times dx. Dx and delta x are always the same thing. See, that's the idea. Is dy and delta y are not the same thing. They're different. you're using dy to approximate delta y. But dx and delta x are the exact same thing. It's just the change in x. So x is 2. So you see, you come down here, so I'm trying to find f prime of 2 times that dx, which is delta x, which is 0.1. So I put 2 into that derivative. 3 times 2 squared minus 2 times 0.1, which is exactly 1, but using 3 decimal places makes it 1.000. So you can see that 1.000 is a good approximation for decent for 1.061. So there's no rule of thumb how close they're supposed to be, but if you get 1.061 for one of them and get 4.258 for the other, you're, at least one of them is wrong, maybe both, but they wouldn't be that far away from each other. All right, here's another one. All right, so y equals 1 over, so I just went ahead and wrote it this way. So dy would be, without the f prime, it would just be the derivative of 1 over x, which is negative 1 over x squared, times dx. I'll just go ahead and jump straight down to the, I guess I didn't have a calculator screen for this one, but it certainly wouldn't have been hard to do. I could put one in there real quick. I'll do the delta y first. So this is, notice it's a negative. So that means your second x value can be smaller. Your first x value can be smaller than the second. And that, in fact, it will be if the x is negative. So 2 plus negative 0.01 would be 1.99. 2 minus 0.01. And then f of 2. So basically you're evaluating this. 1 divided by 1.99 minus 1 divided by 2. So there you see the 00251. Now for the other one. So it's negative 1 over x squared times dx, which dx is negative 0.01. So you have negative 1, x is 2. So negative 1 over 2 squared. So let's do that. Negative 0.01. Paste that in there. So notice the instructions. Always good to read the instructions. 5 decimal places. So for the top one, 00251. And then the bottom one, just to get a 5th decimal place, I just had to add a 0 at the end. Now that one's really close, isn't it? dy is really close to delta y. So that's, yeah. So that one had to be a really good approximation. Excellent. Alrighty, measurement at the edge of a piece of tile is 12 inches with a possible measurement error of 0.02 inches. So we're going to then try to see then what possible error could it cause in measuring the area of the tile. So that's just differential. So if a equals x squared, dA would equal 2x dx, because dA dx equals 2x, bring the 2x over, dx over, excuse me. All right, so x equals 12, dx is, okay, 0.02. I forgot to write the plus and minus, but I put it in the answer. So technically you could say it's plus and minus 0.02. If I could, well, I got it here. I guess I could try to change it. Probably shouldn't have erased that 0.02 because let's see if I can try to grab that. Trying to work my way to get that 0.02 out of there, so I don't have to write it again. There we go. Plus and minus, so then for the area, the actual dA measurement for the area would be 2 times 12 times 0.02, technically, so you're saying plus or minus 0.48 inches squared. Now, the relative error means what is the possible error measurement in the area divided by the actual calculation of what the area would be. So you take a 12-inch piece of tile, so that's the possible, so we could be off possibly up to 48 half a square inch total area off from it based on that measurement error. So what you do is you take that and you divide it by then what would be the calculated area of the tile. Well, so the 144 comes from, if it's a 12-inch tile, it'd be 12 times 12, so it's 144 square inches. So you take 0.48 plus minus, I guess, divide by 144, that gives you 0.0033. And relative error doesn't have any units with it. It's kind of like you're dividing inches squared by inches squared, so it's kind of hard to get a feel for. But making it a percentage error, multiply it by, all you do is multiply it by 100. So we're saying that we could potentially be off by about 1/3 of 1% on our tile. Our tiles could be off by that much. So, is that acceptable or not? I don't know. That's up to you to decide. If you were in this kind of business, I guess it would be. So it's not seem to be that far off. So it's not maybe too big of a concern. So, all right, I believe that concludes. This is the last problem. So, the end.